What we do when we are training is we try new stuff, even though we see some things are better than others, right? There's a McDonald's, there's what's something we like slightly better than McDonald's? Wendy's, Chick-fil-A. Chick-fil-A is definitely better than McDonald's. That's a pretty big gap right there. I'm just putting that out there. But if you only eat at Chick-fil-A, you're missing out. Whereas if you need to do some exploring. If you don't do some exploring, you'll never find the good restaurant. You need to also do some exploiting. If you don't eat at your favorite restaurant, you could be eating at your favorite restaurant, right? And neither extreme will result in you getting a lot of good food in your tummy. So you have to do some exploiting and some exploring. When you turn this thing in, you don't want to be exploring anymore. You want to have a perfectly refined model, and you just want it to balance that pendulum, so you're going to be saying, no, I'm not training now, and now I'm only exploiting. Okay. If you're exploring, and we pick a random number and it's less than epsilon, you see 5% of the time we're going to pick a random action. Is that a good idea or a bad idea? That's not going to keep the pendulum up usually, but sometimes we'll stumble across the right way to keep the pendulum up. Sometimes we'll stumble across saving the princess. Okay. Otherwise, exploit, which means try all the actions, and if it's the best action of them all, hey, that's the one we want. You see how this is look in all of our directions, pick the action with the biggest Q value? Okay. Then we better do the action and let J be the new state. So we used to be down here, far away from the princess. We chose the action of go to the right. Now we're in this state. See how I and J are the states? It's the location of where you are. Okay. And now learn from the experience. In other words, do this equation. All this stuff is just describing the equation to help you understand it. And now let's look at this equation. See, let me put it down low so I can reach up and point. Q. This represents your Q table. In the case of this assignment, that's a neural network. I is the state you're in, A is the action you're performing. Do you remember when we drew that grid, we were saying, what if you're in this state and we go to the right? You see what we're doing is this Q represents that red number that I used to represent if you're in this state and you do this action, how good is it? Q is the quality of the action in the state. See how we have state and action as the parameters? So does it make sense that this is that table value? Okay. This arrow means we're updating what's in that table. So what this equation is doing is it's saying, hey, this is how we learn. If we take all of this stuff and we put that into the table, this is what causes that table to converge to the optimal table, which means we can make the optimal decisions in every state, which means we can save the princess, or balance the pendulum, or do whatever it is that we want to do. Okay, so all we have to do now is understand all of this stuff, and then you've mastered Q learning. Okay. For right now, I'm going to ignore all this part, and let's come over to the right side of this equation. RIAJ. What is R? Reward. This represents your reward. This means if you're in state I and you do action A and that causes you to land in state J, what reward do you get? See how there's actually more parameters here than we're even going to use? We are giving the reward just based on your new state. So I and A here are just there in case your game happens to dole out rewards based on the original state or the action you performed or something like that. There's any number of possibilities here, but however you compute the reward, that's what this whole thing represents. So basically, when you want to give out rewards, give them out. Here they go. What rewards should you use in this game? Let's do the inverted pendulum one, where you're trying to balance the thing upright, the pole. Yeah, it turns out it kind of does. That's the beautiful thing about Q learning. You can pull a heuristic out of the air. Here's your heuristic, and as long as it's not a stupid heuristic, it should work. Now, what do I mean by stupid heuristic? Now you'll think I've called you stupid if yours doesn't work. That's not true. But if you just do how long is it staying alive, that should work. I think a better one is measure the angle, and if it's pretty close to pi, then no, pi halves. Whatever angle is straight up, give it a number, a big number, and if it's down a little, give it a slightly smaller number, and if it's down, give it a slightly smaller number. That's a really good reward system, because that's saying, hey, we like up the best, and we like this kind of okay, and we like this not very good, and this is bad, type thing. Okay. For those watching the video, I was moving my arm in various angles. Okay. Yeah.
So the reward at the beginning initial step will be fixed for all the cells.
Yeah, well, what I'm saying is it's up to you. You can choose a reward system to be whatever you want. And you're going to have to code up something for the reward. But even if you pick a bad reward, even if your reward system is just, as long as the pull hasn't fallen down yet, you get 1 happiness unit. And when the pull has fallen down, you don't. That should work. I think if you do a reward that guides it to know that straight up is the best way to stay up, then that will work even better. But even if all you do is just give it one more, every time frame you give it 1 reward just for still being alive, it should eventually learn that, hey, staying alive is good. That gives me more reward. And then it should learn, in order to stay alive, I have to keep that pendulum as upright as possible, and it should, in theory, still work. So this shouldn't be a really important part of your code, but it can make a difference. So think about the reward a little, but don't sit there tuning it. This isn't, if it doesn't work, this isn't really your problem. Your problem's something else. Okay? Look at what we're doing here. There's a max over b in a of j. A of j here is the set of all possible actions that you can choose in the next state, j. Remember, I is the state you were in, j is the state you're going to. So we're saying, let's think about the future. This is the imagining phase. This is where we look into our future, into our minds, and we're considering the Q table that we already have in our minds. Now you notice here we're updating the Q table based on the Q table. Does that bother you? What we're kind of doing is we're saying, hey, how good we are in our current state depends on how good we're going to be in the future. Doesn't that make sense? If you're right next to saving the princess, how good are you now? Right? We're saying, hey, we're pretty happy right now because we anticipate really soon we're going to be getting it on. And so, therefore, I expected a laugh when I said getting it on. It didn't pan out. Thanks for that courtesy thing. The point is, this is kind of rewarding ourselves, right? It's because we fantasize good things happening soon, we feel like things are good now. And interestingly, that seems to be how the human mind works in a lot of ways. When you're not really happiest when you graduate, you're happiest when you think you're just about to graduate for some reason, because people think, I'm gonna make it, and then that gets the mind excited. So what we're doing here is we're saying, hey, in the future, what's the best thing we could possibly do? We could go left and run into those alligators, or we could go up and get the princess. Hey, that's the one I like the best. See how we're choosing the max here? We're saying, what's the best future we could possibly pick? Because we're assuming we have control over our future. Do you have control over your future? At least to some extent. And interestingly, even if you don't, it works out in these equations, and we'll talk about that. Yeah?
Should it be one state into the future? Or
That's an interesting thing. This is only looking one state into the future. But what it's using is the Q value. And what the Q value does is it accumulates what's in the next state in the future, which accumulates what's in the next state in the future. So what this actually is a recursive thing. We're only seeing one level of recursion here, but that Q value encodes the value of all the way into the future. So what we're really doing here is we're taking one step into the future and we're propagating it back into the current state. Let me put it this way. When the game first starts, I think I erased my game. When the game first starts, yes, I know it's getting worse. The Q value tables are initialized with a whole bunch of zeros or something like unto it. And when our P row, which I'll represent with this circle, goes from here to here and then goes here to here and then here to here, all he gets is a 0, and he only sees a 0 in the future, and he updates it to a 0, and nothing good actually happened. Nothing really happens until he gets to right here and finds the princess, and all of a sudden he realizes, hey, this spot's really good. Did we give it an 80 or 100? I think I gave it 100. I don't remember. Well, it's not until he plays the game again that he comes up here, and he comes up here, and then he goes to the right, and he says, oh, whoa, 0, that way underestimated it. This actually should have been an 80. And it's not until he plays the game again that he's coming up here and then goes up here and says, whoa, this should have been a 64, not a 0. And it turns out that this is why Q-learning is not really the smartest algorithm on planet Earth. He actually has to save that princess 1, 2, 3, 4 times before he even realizes that being here isn't a 0, that you get a 51.2 or whatever it was for going up in that state. What this Q value, this Q update equation is doing is it's saying when you take a step, so if I go from here to here, the Q table gets updated from here to here. And then when he takes a step from here to here, the Q table gets updated from here to here. And when he takes a step from here to there, it gets updated from here to here. And so essentially, every step you take, your knowledge is growing backwards one step. And till you've taken every possible step enough times that the true Q value propagates all the way from the rewards all the way back to the beginning, then the Q table converges, and then it's finally making good decisions. Turns out it takes millions of iterations. You will have to run your code for minutes, and by minutes I mean maybe closer to an hour or ish before you're actually going to get results. This is not a simple problem to solve, but I've given you all the code. Pretty much if you follow the pseudocode and then let it run for a darn long time, it should work. Yeah?
So an improvement on the Q-learning algorithm would be to give it memory of path, so that if you store the sequence of states that you visited so far, then you could update all the Q values in your path each iteration, right?
That is true. It's an improvement in some ways. It tends to converge slightly faster if you do that. If you make it too long, it causes complexity issues. So usually what people do in practice is they'll take only 3 or 4 or 5 steps, and then they'll propagate the value back 4 or 5 steps, but they don't go much more than that. I guess I don't know exactly why. Yeah, that's a slight improvement. At this point, I'm just trying to keep it simple, so we're not going to go there. But yeah, that's a thing. Okay. Do you get that this is the best possible future? And this is what you get right now. This is your reward for what you did. This, I'm going to drop from the equation. This is something we use when we do Q-learning with a Q table, but when we do it with a neural network, we're not going to need this. So, bam, there you go. Let me just show you what it is. See how 1 minus alpha is multiplied by what it used to be? And alpha is multiplied by what we want to update it to? This is just interpolation. Can you see that? Yeah. Okay, so what we're saying is don't update it all the way, just update it a little bit. Why would you do that? Sometimes you are playing a game that's non-deterministic. What if sometimes you say go to the right, but it doesn't actually go where you tell it to go? Or what if the rewards move around or something like that? You don't want to keep updating your table all the way, or else you've learned something that isn't necessarily true. And if you update it just a little bit, it works better in games like that. Okay, well, this game that we're doing is deterministic. Physics is physics, so we don't need to do that. There, now you understand the equation really well, because we've talked about every component of it. Reward for doing what you did, plus the best possible future. That's your new updated Q value. Okay? Now let's talk about doing that with a neural network. Kind of said this last time, but I'm going to say it again. Imagine that there's a function. This function is represented by a neural network such that if you feed in some x value, horizontal axis, you get the y value vertical axis, right? Every time we do this, every time we want to update our equation, we're going to need to get some q values here, right? To do that, we're going to query our neural network. We're going to say, okay, if I'm in this state and I do this action, what's my new q value? So input is state in action, output is q value. Okay? So I'm going to query my neural network for all possible actions and get all those q values from my table. And then I'm going to add my reward to that. And then I'm going to update my table. How do I update my table when my table is a neural network? Yeah, I call this train incremental function, which updates it a little bit. So it does some math, and then it computes that, hey, for these input values, I and A, which we'll say is somehow represented by this spot right here, the new point should be there. And when you train it, that basically tells the neural network, imagine that this is a big sheet of aluminum. And imagine you have a hammer. It basically goes to this spot, that input spot, and it gives it a good whack. And it says, go towards that point. Okay? So you say bang, and now all of a sudden the new neural network looks kind of like this. Right? Okay? That's what it does. Now, when you train a neural network, you get to tell it the direction in which to hit with the hammer. But you don't really know how far to go with that hammer. This is something we call the learning rate. If your learning rate is too big, you might end up doing something like this. That would be bad, right? Too much. If your learning rate's too small, you'll make very little change. So how do you know what learning rate to use? That's the problem. You don't know. 0.03 usually works pretty well, and do it a lot of times. As long as it's kind of small and you do it a lot, you'll kind of start, this piece of aluminum will start bending and bending until it gets to what it's supposed to be, and then the thing will work overall. Do you see how that kind of accomplishes the same thing as this partial update step in the equation? Because we're using a neural network that bends slowly to fit what you're supposed to fit to, it doesn't learn. Even though we've computed the true value we want to put there, it doesn't learn it all the way. It learns it just a little bit. And so it kind of takes care of that automatically. One of the great things about using a neural network is some learning has occurred not just at the very point where we are, not just right here, but right around here it kind of bent up too, right? What that means is, hey, when we're in a state kind of like that one, it figures that something similar must also be the case there too. Now sometimes that's wrong, and we'll train that later by hitting it with a hammer over here, and it'll have to learn to bend like that. But what it does is this enables it to generalize, and so it starts ultimately learning faster than if you use a Q-table. Okay, I have talked myself out of time, so I'm going to have to let you go, but I hope that's enough. You can get started. We'll talk about it again some more Monday and Wednesday, and hopefully by the coming Friday you'll be able to actually make this thing work. Thanks for coming. Please feel free to post questions on the forum.